All right, Chris, what do you say we hit it? You ready?
Yes, I'm ready.
All right. Well, welcome, everyone. My name's Mark Hughes, and I'm part of the team at Royal Circuit Solutions in Hollister, California, the original quick-turn PCB experts. We've been making quick-turn PCBs for the last 15 years, and when I say quick, I mean quick. We can turn out some jobs inside of a single shift, and those are prototypes. So if you have any PCB needs, please feel free to reach out to us. We'll have the information at the end of the webinar and who to contact. All right, we've got very exciting news today. We've got Chris Hunrath from Electro, an absolute genius when it comes to PCB laminates. This guy has just an encyclopedic knowledge of PCB information and laminate material information in his head. It's really a wonder. So we're really glad to have him here with us today. As we go along, Chris is going to take some questions in the question and answer portion of the webinar. Down at the bottom of your screen, you'll see a little Q&A in chat. Please use Q&A to ask questions. That will be the only screen that is monitored for that purpose. We've got 2 employees that are going to try to type answers as well as moderate the discussion. So keep an eye on that. We will record this webinar and post it at our blog within the next 1 or 2 days. We'll also ask Chris if we can make the slides available to you at the end of the webinar. With that, it is my great pleasure to welcome Chris Hunrath. Tell us a little bit about yourself and what we're going to do today, buddy.
Hey, thanks, Mark. Hopefully I can live up to your description. So I've been in circuit boards going back to multi-wire technology since 1983. Currently, I've been with Electro. Actually, I just hit my 19th year with the company, and we're a material supplier. And our goal is to provide materials in a quick-turn fashion, but also provide technical expertise. I consider some of the folks in the company material scientists. And as circuitry gets more complex, the nature of the materials becomes very important. So we have 10 branches across the US, 1 in Canada, and we supply all kinds of materials to make printed circuit boards. One of the things that we've been doing for about the last 10 years is something called ACT, Accomplish Change Together. That's where we actively work with our customers, like Royal Circuits and their customers, to find the best solution for challenging electronic applications. So just a little history on circuit boards. Circuit boards have been around. Some of the patents go back to the 1920s. But before circuit boards, things were hardwired, and that's a mess, both from a reliability standpoint, but also from a mass production standpoint. I actually have an old antique stereo, which I enjoy. I found it in Boulder Creek. It was in very good condition. It's a tube stereo, and yes, it does not have a circuit board. So working on it is a challenge, but I do enjoy playing some old records on this system. So going back to the 1940s, and I mentioned some of the patents go back to to the early 20th century. There are lots of different ways to make circuit boards, but the idea is to be able to connect components together. In the beginning, it was single-sided, and then eventually double-sided, and then eventually multi-layer. And then, of course, I have a customer that builds 90-layer multi-layers. Those are chip test boards, and because of they're trying to test the entire wafer, multiple chipsets, they need a lot of IOs to be able to test the PCB. So you can see boards can run from very simple to very complex.
Chris, I need to stop you for a second. I don't think I heard that correctly. Did you say 90 layer?
Yeah, 90 layers, 90, yes.
Wow. Okay.
Yeah, and circuit boards can be everything from backplanes to printed electronics, rigid flex, heaters, and then in the lower right corner you see those are chemical sensors for wearable electronics. So and we have technical information on each one of these technologies. What you don't see pictured here is fired on technology. That's where conductive inks are screened and then fired to form the metal circuitry with ceramics. Whole nother technology, whole nother subject. But that is something that we do supply to the industry. So one of the goals here, and really the goal today, is for design success. I've heard in the industry that about half the designs don't work properly the first go around, and our goal is to help the industry hit the ground running, so to speak, where you have a design, you have a goal, and working with the fabricator and the material supplier, we can give you guys a greater chance for success the first time, get your product to market sooner. And you don't have to be material science experts. That's our job. That's our passion. That's what we do.
That's pretty cool. So let's say I'm doing a design and I'm having a little trouble. I just call you up.
Yes.
Is that simple?
Yeah, it is. Or one of my colleagues. But yeah, that's a lot of what we do. I interact with the fabricators and their customers all the time, which keeps me quite busy and happy.
Oh, all right.
So in the most basic form, PCB laminates have been based on fiberglass reinforced composites. This has been around probably in its current form one way or another since the 1940s. However, the resins have changed. Even the glass fabric has changed to meet the technology needs of today. And of course, with higher bandwidths, RF, Internet of Things, 5G, the materials are becoming more and more important. So just a common building block in a multi-layer PCB is a thin core dielectric. Fabricators like Royal Circuits actually can make their own laminate, but they don't. It's cheaper and easier to buy it prefabricated. What they will do is they'll put design-specific circuitry on the core material and then laminate them together to make a complex PCB. And that's really that's their expertise. So that's where we leave off, and Royal Circuits picks up is to turn the core material into a web of circuitry. And there's a lot of attributes to the material, and again, that's where we work together to get what you need.
Hey, we've got our first question. You ready for it?
Sure.
All right. Is resin the same as pre-preg or the bonding material between layers?
Good question. Actually, the resin is the bonding agent or glue, if you would, and the fiberglass is the backbone. Pre-preg is the same material as the core material, just in an uncured state. So we would call that B stage, where C stage would be cured, B stage would be uncured. Pre-preg is used to make the core, and then pre-preg is also used to make the multi-layer circuitry, to bond all the core layers together in a stack up. I've got some good images coming up on that.
All right, thanks, Chris.
Very, very common is to have interleaved signal circuits with reference planes for strip line and controlled impedance purposes. More on that later, but this is not an uncommon building block where you have the thinner copper for the signal circuits and the thicker copper for either power or ground on the other side. So what Royal Circuits does, as I hinted to earlier, is they'll take these blank cores that we supply, to our customers, and they'll turn it into circuit patterns. You'll see in the lower right there, that has also been through a bond treatment process. So when they laminate all the layers together, the adhesion is very good, and the part survives not only assembly, but decades of use. You can see also too, there's some test patterns and coupons on the edges of the panel. That's a 2-up panel. It could be 1-up if it's a large circuit board, or it could be 30, 40, 50 up if the boards are tiny. But it's more efficient to put multiple circuit boards on one panel.
That's because you can't just make a small portion of the panel. You've got to make it all at the same time, right?
Right. It's just, it's more efficient. And yeah, it's hard to handle. I mean, I've seen parts that are tiny. You just simply can't handle them through the process equipment in the PCB shop. So just some examples of a 6-layer simple PCB, and there's a 72-layer PCB. Unfortunately, I don't have a photograph of a stack up on a 90-layer board, but I assure you our customers do build them, not very often. The 72 layer PCB actually has 35 VGAs on it, and that's what's driving the layer count up, is the quantity of VGAs. And that actually that board was made out of 4 18-layer subs that are layered together or bonded together later on in the process. Quite complex. I believe the board's somewhere around $30,000. Expensive PCB.
Wow.
And by the way, that board, I believe, is used in design systems that design other PCBs.
Really?
Yeah.
Can we go back for a second? How do you bond those intermediate layers together? You said it was made out of 18-layer subs?
Yes. And doing subs are not uncommon. What's a little uncommon for this board, and it's a newer technology that's being more and more utilized, is that's using a low temperature sintering conductive paste to link the layers together. A little bit more on that coming later in the presentation. I'll talk about that technology. Again, a technology that could have its own presentation.
Okay, hey, we've got another question. Mitch asks, the slide that showed the detailed dielectric material, is there a reason it's stated normally 3 to 8 mils? I'm sure there's other thicknesses, right?
Yes, good question. Yes, so on a multi-layer board, there are some form factors that have to be achieved for the end product or the housing or device that the board will go into. So when you're doing complex multi-layers, you want the individual layers to be on the thinner side. It also has to do with controlling impedance, and managing the electrical properties. But those are common, 3 to 8 mils. Yes, you can have a board that is 062 double-sided, or what we call 059. It's 062 with the outside coppers. Typical double-sided form factor. Kind of less common these days as circuits have become more complex. The other thing you want to keep in mind, and I'll talk about this a little bit further, is when you have power and ground planes, you don't want to use a thick core. That has to do with in-plane inductance. That creates problems in digital circuitry. And again, I'll talk about that some more down the road. But thinner cores are better for packaging and fitting everything into a desired thickness, and also for certain electricals.
All right, we've got one other question that I think I'll field. It says, is there such a thing as a standard stack up, or is it manufacturer dependent? From my perspective, and Chris can chime in on this because I just worked for one board house, he works with lots. It seems to be mostly fabricator dependent. I mean, everybody kind of has the same idea. Maybe you do a 1/2 ounce multi-layer with some pre-preg, non-impedance controlled, but basically the manufacturers are trying to come up with something that works for the majority of their customers, so that they can then perhaps gang multiple jobs onto the same panel. If you've seen Osh Park, that type of thing, everybody's using the same stack up in that design. So Osh Park sets it out, and you go for it. One of the ways, or one of the times, you can use that type of stack up, if you can make your design on a solderless breadboard, you can pretty much just design for connectivity. You can use any stack up that's out there. Chris, did you want to add on to that?
Yeah, I think rather than a standard stack up, there's standard building blocks. So I think, to build on what you were talking about, Mark, 1/2 ounce copper is very common for signal layers. 1 and 2 ounce are common for power and ground. And then, as I mentioned earlier, thin cores are common for multi-layer stack ups. Beyond that, it's not that important. Certainly, I've seen OEMs go to fabricators where they have their standard build, and the circuit pattern will vary, but the standard build will stay somewhat the same. But I think because of the applications vary so much, the stack ups will vary also. I don't think that's necessarily a barrier or a issue, because the design software that the PCB fabricators work from is pretty flexible.
All right. Thanks, Chris.
So just some via structures, for the folks that maybe are not familiar with the layers inside a PCB. We talk about blind vias, buried vias, through vias, because most of the technology these days is surface mount, with the exception of things like connectors and power connections. The plated through holes are there just to link the layers together. And you can see in the lower right, you can see a side view showing where the circuits are literally floating in the dielectric after lamination. It just gives you an idea of how the circuits are formed in stacks and layers and then electroplated. Just a little trivia on plating. You can't electroplate a non-conductive material. So PCB shops use technologies to put a very thin deposition of a conductive material down, and then they'll electroplate on top of that. That technology actually goes back to 1849 for something called a failings test that was used to test for diabetes. And that technology eventually led to mirror manufacture and then eventually PCB manufacturing. So
no kidding.
just a little trivia on a little chemistry trivia. If your blood produced a reducing sugar and you mixed it with copper oxide or copper sulfate, and you heated it, it would plate out copper. And that technology, a similar system was used for with silver bearing salts, but same idea, same test, and that's how that technology was born. So one of the things that's driving layer count ups is the invention of the BGA. I think the BGA is something that's been not overlooked, but underappreciated. When chip packages got to the point where you didn't have just leads around the edge, you could put leads underneath. You saw an explosion in IOs, and therefore it drives layer counts up. Sometimes we try in a PCB, we try and fit 10 pounds of circuitry in a 5-pound stack up. And then in the lower right, you see 9 layers of circuits and 12 mils of overall thickness. Some of the dielectrics there are 9 micron. So you can make things very, very small. Not new to the chip world, but in the PCB world, doing something in that kind of density is special.
Right. I like the Mythbusters reference there, buddy.
Yeah.
And
they shop at the same store.
Yeah. I was just going to point out too, I said you had an encyclopedic knowledge and you're like, oh no, maybe I don't. You just busted out some pretty intense history there, Chris. That was impressive.
It's like I said, it's my passion. So just some important PCB material attributes: glass transition temperature, TG, decomposition temperature. From a designer standpoint, not necessarily the most important thing to know, but it is important to know the whole system, depending on what kind of device it is. These things are important for both electrical performance and reliability. And reliability sometimes is just getting through the assembly process, because if you don't have these things right, you could end up with a design that doesn't get past assembly, which is a big problem. So again, that's where we're here to help. Because when you guys are successful, you'll do the next design, the next design, the next design. So it's good business for all of us.
All right.
So really, expanding on that a little bit is why and how we choose a PCB laminate. Impedance control is one, and that's driven a lot by dielectric constant, thickness, trace width. There are other attributes, but we might, because we have to hit a particular target impedance and we need to do it in a particular form factor, we might pick a low dielectric constant laminate because that lets us get a higher impedance in a thinner package. So that's just one example. The loss of the material, and I'll talk more about the signal loss later on, but one of the things that that we hear a lot about is that the fact that the signal actually, the energy of a signal actually lives in the dielectric space. It lives what we call the white space in a schematic, not necessarily in the trace. That's where the field lives. Sure, the trace is the waveguide, but the dielectric is the area where the field lives. So that's very important. And as frequencies and speeds go up, that becomes more and more important. Skew control. We didn't. Years ago, we didn't care about picosecond timing in a differential pair. Now we do. Embedded passives, again, a whole nother area of technology that we can get into and deserves its own presentation. So maybe that would be a follow-on, technology presentation. And of course, cost and availability. I've seen people call out some very exotic materials over the years, and if it's very difficult to get, might be a showstopper. And of course, cost. You know, the overall idea is to make the part reliable, perform, cost sensitive, or cost sensible, I should say. And you know, of course, the other aspect is timing. You know, quick turn PCB. One of my goals is been to make sure our customers can get materials so they can capture 3-day turns. So that means they need material the same day.
All right, Chris, I've got a quick question. We've actually got a couple here, but this one's specific to this slide. Question is, lower DK also means lower DF in general?
In general, they're not directly linked, but typically lower DK materials have lower loss. Not always the case. There are some acrylics with low dielectric constant and relatively high loss, so they're not always linked. But in general, the lower DK materials tend to have, PCB materials tend to have lower loss.
All right, and then we've also got, what is skew control?
Okay, so in differential pairs, it's important to have the signal velocity or signal timing the same. And when they become skewed, in other words, the transmission speed is different, it can cause data issues. Again, more on that. I actually have a section in this presentation on skew control.
Okay.
So dielectric constant, just to expand on that a little bit, dielectric constant will vary within the same material, and that's because it is sometimes impacted by glass to resin ratios. PCB materials are composites, so that's important to remember. They have composite properties. Just a little note on composites. We use composites in technology, you know, beyond electronics, because we want to get different properties out of a material. So, you know, just, you know, in an example of a PCB material, the glass provides CT control, it provides strength, it also provides a substrate to, you know, support everything through the manufacturing process. The resin actually provides the bonding, it provides the seal, if you would, it provides the dielectric. So we're trying to get different properties from different materials. Some materials you want to get opposing properties, and you can get there because of using the use of composites. Moisture and temperature can affect some of the properties of the material. We have a lot of data on that. Again, that's where we could help. If you, let's just say you're building an RF device and you want to know how it's going to perform outdoors, we have that data on those materials.
How big of a change is it? How big of a property change do these materials experience in the various environments, say outdoors versus, I don't know where else you might put one, but let's say automotive, like a RF design?
Yeah, so it really depends on the material. Some materials will absorb a lot of moisture, and if they're in a humid environment, their properties will change, and some materials don't. Again, that's why it's important to know the application and to know the material. But some of the changes can be large.
Okay, thanks, Chris.
So just a little bit on dielectric constant. Again, this is where it's important to work with the fabricator. They have software tools that will predict dielectric constant based on the stack up and the resin to glass ratio. And we provide the data on the individual materials, and then they in turn use that in their stack up tool to predict the dielectric constant and the impedance. The glass to resin ratio in general, higher resin, lower decay, higher glass, higher decay. So glass to resin ratio is important, but there's also mechanical aspects that drive glass to resin ratio. So just some basic categories in HSD materials, and what we call HSD is high speed digital or high bit rate designs. We also talk about high frequency designs in the RF world. And this is just showing there's tiers of material. So FR4, again, been around a long time. FR4 underwent a big change in 2006 when lead-free came about. We started using phenolic cured FR4. to get higher thermal performance to go through lead-free solder assembly, because the temperatures are higher in lead-free. But then as speeds went up and bit rates went up, we needed lower loss materials for higher performance.
So Chris,
Yes.
I was going to ask, how many FR4 materials do you think are out there?
From various manufacturers, hundreds. That's where this can get complex. We actually sell 31 different resin systems on the rigid side. That's not counting flex, but we really mostly support and stock 9. And the reason why it's only 9 is because some of the older systems out of that 31, there are better performing materials out there, so there's no need for them. We support them for legacy designs where it's locked in for either a medical or aerospace or military. They can't change. But we support 9 systems where we stock and have that on a regular basis. And that covers everything from economical products to high performance to high thermal. So that, again, that's where we work with folks like, like Royal Circuits to help with the choice of materials.
Right, thanks, Chris. We've got a question that, and by the way, for those of you asking questions, I'm trying to limit it so we can get through all of these slides. So not all the questions are getting answered here, but we will save them, and they get saved into a document for us that we can go back to later. Fred asks, are these tiers created by industry standards or by individual laminate companies?
Individual laminate companies. So this is not, for instance, an IPC, and I don't know if anyone's familiar with IPC, but IPC sets standards. The IPC laminates in the 4101 spec, which is for PCB rigid materials, go by slash sheets, and that gets very complicated. That's the purpose of this slide and this diagram, is to kind of simplify it into groups. So this is not an industry standard tier system.
All right, thanks.
Glass fabrics, as I mentioned before, are an important part of the PCB, not used in flex, just FYI. But glass fabrics right now are in 2 major categories, what we call E-glass and low decay. And then within those categories, you have standard and spread. More on that, but really with the formulation of low decay glass, it allows us to make thermoset resin systems that have electrical performance similar to Teflon. Now, Teflon, most people probably know Teflon as a non-stick coating, but you can also make PCBs out of it, and it has some very interesting properties, some very good properties. It's also very difficult to work with on a PCB standpoint, from a PCB fabrication standpoint, and it even has some challenges in use on the assembly side and so on and so forth. So to have thermoset, more standardized operating materials have electrical performance similar to Teflon is a big advancement. And again, more on that later. So again, designers and OEMs don't need to become PCB or material experts. I just want to give you guys a flavor of some of the stuff that we work with. These are standard fiberglass weaves. So in other words, the glass fabric can vary in thickness, and these are building blocks to make a complex PCB. Could be could be the thicker glasses like 7628 if it's a simple double-sided board, or it could use the 106 if the board layer count's high and you need thin layers, or if it has thick copper. And Royal Circuits does probably more thick copper work than my other fabricators, so they use this as building blocks for filling the thick copper circuits.
Chris, we've got a question from Ray. Does pressed thickness for pre-pregs stated in data sheets for 100% copper coverage change in actual stack-ups with less copper coverage? So I think the question is, if we've got a stack-up and we are, heavy copper, whatever, and we remove a ton of copper, how do we maintain board thickness and planarity?
Well, so that's a great question, because yes, the prepreg per ply thickness will change if you have a lot of open space that gobbles up resin. So if you look at the DKDF charts that are very common from the laminators, the laminate suppliers, they will have what they call scale flow thickness for the prepregs. That is assuming that the copper is 100%. So the thickness will be lower, and the amount etched will change that thickness. Again, the fabricators like Royal Circuits will have a calculator that will estimate the thickness based on the amount of copper removed. And that's where you would use the different building blocks of prepreg to get the desired thickness. So let's just say, for example, you need a 4 mil gap. You might use 2 plies of 106 prepreg instead of 2 plies of 1080 to provide the fill and to get that 4 mil thickness. So calculators are used to take that into account.
Right. Thanks, Chris.
Relatively new are the spread glass prepregs. They are primarily there for signal performance purposes. We talked a little bit about Skew earlier. I'm going to talk more about that. Really what it does is it provides a uniform micro decay effect. So if you remember the previous slide, in fact, I'll go back. If you look at the 1080 and 106, you see open areas. Imagine if you would a trace going over the open areas and versus a trace that's going over one of the glass bundles. You could see that they would have different dielectric field effects around that trace, which would change its propagation velocity of the signal and could cause skew on differential pairs. Spread glass is much better for that. Spread glass is not good for everything though. If you're doing thick copper, let's say you're doing some 4-ounce power planes, you want the open weave so the resin can come through and fill the open areas. So really, again, this is where the fabricator's expertise comes in and uses the right building blocks to make the PCB. So a little bit more on Skew. You can see in the lower left a diagram of what a differential pair would look like. And ideally, the upper left is what you would see in terms of the propagation speed between the two signals. And then you can see as Skew gets worse, you see a shift in the speed, and then you end up with a delay in picoseconds. And obviously, if it gets to a certain point, the system won't work properly. So again, using spread glass will make the decay effect more uniform, and you'll have uniform signal propagation between the two traces. So
Chris,
yes,
sorry to interrupt, but we had a question from Dylan. He asked, what's the best weave for high-speed differential pairs?
So mechanically spread. So I'm just going to go back. So these mechanically spread weaves are much better for skew control or skew reduction. And in general, 2 plies are better than 1. So in other words, if I use 2 plies of 1067, that's going to give me a very uniform micro decay effect versus the open weave prepregs. Again, these have their use as building blocks, but because they can deliver more resin, especially for thick copper, but for high frequency and differential pairs, the spread weaves are much, much better. One of the solutions used to be was to rotate the circuit pattern in the panel, but that creates a higher material cost. So if it's done at the fabricator or if it's done at the material supplier, you end up throwing away a lot of material that would otherwise be used, and it increases the cost. So the spread weave is a much better solution to help with the skew control. So just kind of a review of some of the things we've talked about. This is where the designer and fabricators need to collaborate. I think that I see that a lot today, but there are cases where I've seen a design come through a PCB shop and things weren't considered that end up being showstoppers. So overall goal here today is to hit the design success right from the start. So just some of the other material properties. Moisture absorption, we talked a little bit about that and how that can affect both dielectric constant and loss. Time to delam, that's very important for assembly. That rates a material or a PCB stack-up performance in thermal excursions. Typically a small sample is heated and then the change in the z-axis is measured. UL rating, that's important for some OEMs, less important for others. Primarily very important for consumer electronics, the UL rating. Most laminates are flame retardant. With halogen-free materials, the flame retardant is non-bromine. For standard materials, it's brominated. There are some toxic bromine compounds. They haven't been used in decades. Again, we have lots of information on that. If that ever comes up, just reach out to myself or one of the folks at Royal Circuits. But really what I want to talk about also is dissipation factor, signal loss. When you think of high-speed digital or RF terms, again, the field lives in the dielectric material. So if that material absorbs some of the energy that's given off in heat, and then you lose some of the signal performance.
Very interesting. Thanks, Chris.
Just to introduce eye patterns, eye diagrams. You can do these simulated, or you can actually measure these with something called a BERT scope, network analyzer, or VNA. These are tools that experts use to evaluate either materials or particular design. And really, what it's doing is it's pumping a digital signal through the transmission line, and you're looking at changes in the velocity and also the rise time. And if the eye starts closing in, that means the signal is not performing well. You could look at things like jitter and other attributes. Just wanted to show an example of, this is the same circuit just pumped up at higher frequency. This is a great example of why you don't want to use FR4 at high frequencies. And this is a relatively short trace. This is only 4 inches. Now 4 inches might sound like a good amount of trace distance, but remember that's 4 inches throughout the circuit. If you look at a circuit board in the web of circuitry, you can sometimes have miles of circuits inside the PCB. So you can see the eye start closing in as you go higher in frequency. If this were a 24-inch trace, in other words, or net, going through the PCB back and forth, you would see the eye completely closed in at 5 gig. It would be completely washed out. So it's just an example of how the materials and the frequency change the performance at high speeds.
Chris, I've got a quick question for you. Back at, gosh, what was the last show we attended together? Was that PCB, what? No, that was DesignCon. DesignCon had the PAM4, the latest PAM4 spec. They're doing something crazy, like 112, gigabits per second. And they're not really using any exotic materials. They're not using the Teflon boards, the spray glass. They're just doing something now called signal recovery. And that was the first time I'd ever heard of it. Have you any experience in this at all?
Yeah, a little bit. Yeah, so the way I understand PAM4 and going back to digital signals, 1 and 0s are expressed with, either 0 volts and plus 5 volts, just to use a very basic example. So if you were to look at, let me back up a little bit. The difference between an oscilloscope and a multimeter is an oscilloscope measures voltage over time. Even when you're measuring other things like current or signals, they get converted into a voltage that the oscilloscope will read. And it's showing basically, like in a graphical format, it's showing the voltage change over time. So if you look at these BERT scope scans here, the bar at the bottom is 0 volts and the bar up top is, let's just say for example purposes, it's 0.5 volts. You can see the time it takes to go from 0 to 0.5 volts is expressed in a slight curve. And if it were a digital wave, square wave, it would be perfectly vertical. But in reality, that doesn't happen. There's a time delay because it takes time for that trace to go from a 0-volt state to a 0.5-volt state. I know I'm kind of taking a long route to explain this, but my understanding of PAM4 is instead of going from 0 to 0.5 volts, you would have steps at different levels, and each one would be a different digital character.
Yeah, that corresponds with what I understand as well.
So yeah, so you can use PAM4 at lower frequencies and make it work. So if I use 1 gigabit, if my speed is 1 gigabit, but I slice it up into four steps, it might work just fine. So, and I'm carrying 4 times the amount of data in the same time period. If I have different, maybe not the same time period, but with a slight time shift. So that could work. But if I go higher in frequency, the noise margin or sorry, the loss margin for PAM4 is even less than it is for, you know, a standard digital signal. So PAM4, I think, is something we're going to hear a lot about. I think with software and what you talk about data or signal recovery, that's how, by the way, software and signal manipulation is how we're getting speeds in standard PCB materials in copper as high as they are. I mean, we can get 1 gigabits per second, I'm sorry, 100 gigabits per second out of copper. There was a time in the industry where we thought 1 gigabit would be the limit, and everything would be beyond that would be fiber optic.
Yeah.
Software systems are very much an integral part, as much as the materials, in how we can make high-speed digital circuits work. So I don't know if I answered your question properly, but
no, I think you did. So something I hadn't considered, you know, even though we're seeing, you know, 12, you know, I think we're looking here 12.5 gigabits per second. If I understood you correctly, so we have the, you know, the 4-bit levels that we can be at. I don't need to be, you know, let's say transmitting it at 10 gigahertz anymore. I could knock that down to 2.5 gigahertz and still get the same data rate.
yes.
As an example. I gotcha. Okay, that's it. I don't know why I didn't think of that myself, but
yeah,
I appreciate you answering it.
Yeah, but as you go up in performance, you're going to need both, and that's where you'll need lower loss materials. So, you know, our society is data hungry, right? So bandwidth hungry. So I think we're going to see the limits pushed. And PAM4 could potentially be a big boost, but I think we're going to keep pushing forward.
Got it. Okay, thanks, buddy.
So just looking at the entire system, you know, the signal loss is a combination of both the dielectric and the copper or the conductor. Conductor loss becomes a bigger factor above 10 gig. Dielectric loss is important at all levels. It really depends on the type of material and the circuitry. But a lot of times, signal loss is the most important thing, even more important than controlled impedance. And high frequencies, you have to consider the loss of the circuits, and that's where really a PCB becomes part of the design. It's no longer just a wire to connect point A to point B. It's actually an active component. Just a real brief overview on resins, and you know, again, I'm sure most people on this call don't want to become you know, material chemists or material scientists, but there are different families of materials with different properties, and we use these sometimes in combination to get the end properties in a PCB. One of the things that's been a big improvement over the last I would say 5 to 8 years has been the use of polyphenylene oxide or PPO blends, because you can, with the right kind of fiberglass, you can get Teflon or PTFE type performance without some of the drawbacks. And those are materials that have been, one of our products has grown by 400% over last year, and last year was double over the year previous. So
wow.
Big growth area for us. It's still not our most popular material. Our most popular material in terms of volume is still FR4, but the other materials are growing rapidly, and for good reason, because people want to get more speed out of their PCB designs. So FR4, it's been around for decades in one form or another. Currently, the most popular flavor is a phenolic cured epoxy with a talc filler. You know, you guys, Royal Circuits folks, are a great customer of ours for this product. We sell this a lot across the U.S.
Yeah, we've got shelves and shelves and shelves of it on hand, buddy.
There's been some changes in the IPC slash sheets. I don't want to spend a lot of time on this, but again, this is where we can help. But there's filled and unfilled systems, and if you look at the lower picture, you can see little tiny flakes of talc. Fillers can be used for changing the electrical properties, but more often than not, they're used for lowering the CTE of the material. And more filler can also lower the cost of the material, depending on the filler type and the resin system. So sometimes it's used for cost, sometimes it's used for thermal performance, sometimes it's used for electrical performance, depending on the filler.
All right.
So a little bit now on copper foil. Again, copper foil, at one time, the limit was touted at 1 gigabit. We've gone far beyond that. Copper foil does come in different flavors. One of the things you'll probably hear is VLP or VLP2 or HVLP. Really, that talks about the profile of the copper or how rough it is. What you're seeing on the left-hand side is an SEM of the copper surface. And more on the copper in a little bit, but I do want to talk about, this is a Wilkinson divider. I don't know if anyone on this webinar is familiar with it, but this is a case where you're actually forming devices out of the PCB material. In other words, the copper trace is forming the divider. Typically, RF structures are on the surface layers, either one or both sides of the PCB. Not uncommon to hybrid FR4 with a low loss material on the outside. That gets you kind of the best of both worlds. It helps mitigate cost or manage cost, but gets you the performance you need on the layers that are doing the transmission. In general, we talk about HSD or high-speed digital as signals that stay in the PCB, that travel on transmission lines that go between devices, and RF designs are where you have signals going in and out of the board into the surrounding environment. And we have materials, you know, for that. I've listed a few here, and we have, again, lots of data on how these materials perform in different environments. So copper foil is made in a couple different ways. The predominant manufacturing technology used for PCB is a large stainless steel drum rotated in a copper bath. I can tell you that if you walk by that plating operation and you have metal in your pocket, you might be in trouble because it's done at very high current. As a drum is rotating, the foil is peeled off, and then that foil is treated in several ways to make PCBs. To make that foil smooth, some technology is used to make low loss circuitry, but I can tell you that this foil is used in other systems as well. Battery technology has really advanced in the last couple of years, and it's a big consumer of this type of copper foil.
Chris, I just want to be respectful of our participants' times. We're going to keep running this as long as you guys are willing to listen to us. There's about 10 slides left, just to let you folks know so you can plan your time. All right, go ahead, buddy.
So copper foil becomes important for high frequency signals, just like the dielectric, just like the loss tangent of the materials. And as frequencies go up, I'm sure most people are familiar that it pushes the energy into the surface of the copper. We call it skin effect, and that's where we want to get smoother copper foils for high frequency circuits. For things like FR4, it's not critical, but when you start going into lower loss materials, you want to make sure you use a smoother copper. And again, this is something that we work closely with fabricators on. Becomes a big factor as you go higher in speeds above 10 gigahertz. We don't need to waste a lot of time on this, but anyway, this is just some copper foil nomenclature. VLP, HVLP, VLP2.
What are those, buddy?
Well, very low profile, hyper very low profile copper, very low profile 2 micron RZ max. Again, this is something that we could help with if there are some questions. I did want to show this slide though. These are all at the same magnification. These are just different SEMs of copper foil, and you can see how the topography changes quite a bit.
Wow.
And obviously, higher performance, higher speed circuitry, you're better off with the lower profile copper. Now, you will have lower peels, so using that on a surface where you have components is something that needs to be considered. Whereas if it's an internal layer, it's probably not a big issue, but copper foil profile is very important.
Interesting. Okay, so if I'm designing a stack up and I've got something where I need, you know, the real smooth copper to avoid losses, I would just drop those down from the top or bottom layers into an internal layer, use the very, very smooth copper till I, you know, run it to wherever I need to run it. While on the outside, I'd maintain the thicker, the layers with the larger dendrites, just to keep everything on the board.
Right, and that's very common to use standard foil on the outside and use for the transmission lines, especially in a strip line system where you know, you have a reference plane on both sides of the internal layers. You know, using the smooth copper inside is beneficial. There are a few exceptions, and I'll give you an example. If you have an RF design, you still may want the smooth copper on the surface because it gives you better transmission properties. But you also have to know that if you put components elsewhere away from the radiating device, you will have lower peels, and you need to make sure that the components aren't in a system that might be vulnerable to some mechanical action.
Interesting. All right.
Just a quick note on polyimide material. Polyimide is still the best material for high temperature applications. Actually, Isola just came out with a new benzoxazine based material that's second to polyimide, but very close. It actually has some benefits over polyimide. It's less brittle. It's good for filling thick copper. That's something I think we're going to see in automotive applications. You know, as that material becomes more commercially available. But polyimide is still used on downhole and aerospace and under hood, and it is a very good thermal material. So just kind of review some of the things we talked about. These are important questions, you know, for the design and for the fabricator, and this is where we can help. So density, speed, controlled impedance, what's the operating temperature? Is it heavy copper? Is it high power, high voltage? Just for example, I've seen some applications where someone needed 5,000 volts between planes. We have a material for that application.
You're kidding.
Yeah, that's a very interesting application. Just some other PCB technology. Again, each one could be worthy of a presentation. At the top right, that's embedded capacitance material that lowers in-plane inductance and removes surface capacitors. Very underutilized technology, although it is growing. There are film resistors. In other words, you can have a layered system where you have nickel chromium on the backside of copper foil, and you can selectively etch and print resistors that become part of the inner layers. And then in the lower left, you see stacked vias. Though that was done in one lamination cycle using a special paste.
Wow, that's incredible.
This is something relatively new. The technology itself isn't new, but the materials we have to do this is something called MSAP, or a modified semi-additive process. We have a 1.5 micron foil on a half-ounce carrier. You can laminate it, peel off the carrier, print it with a special high-resolution circuit, and you can see 15 micron lines and spaces. So that could be done in a standard PCB shop now.
Wow. That's amazing.
just a quick overview on flex materials. Kapton is a polyimide film invented by DuPont. Been around a long time. Was originally used in spacesuits. That was later replaced with Kevlar. Kevlar replaced the Kapton inside the suits as a micrometeor barrier, but it's still extensively used in space for other applications. It's in the Mars rover. It's in all the rovers. It's in the solar panels in the rovers, but it's also been used in other space applications, and that's because it's flexible and you can package it tightly and then deploy it once it reaches its destination. That's for both satellites and, again, the rovers. We're seeing an explosion in flex circuits in the medical industry. It's in the Da Vinci robot. It's in all kinds of instruments. It's in implantables. It's in all kinds of things. It's also been used in downhole exploration, undersea environments. Flex has been used in a lot of applications. Just wanted to briefly go over flex materials. There are different types of materials. Royal Flex has experience with these. So you can have your basic single-sided all the way through rigid flex designs. And the material sets are a little different. You can use flex materials with rigid materials in a non-rigid flex design. And that one example I gave about a 5,000 volt withstanding voltage. One way to do it is to put a flex material between your power planes and a PCB. So you can mix and match the flex materials with rigid PCB materials. Kapton's been the backbone. It's because it has great XY strength without glass fabric as a reinforcement, and it's been used extensively. Kapton's actually a pretty amazing material. It has a decomposition of about 1,000 degrees.
Really?
Yeah. So it's a pretty good material for other components of the flex stack up won't survive that, but the Kapton itself will. And just flex material building blocks, just wanted to make sure folks were familiar with the different building blocks. But again, that's just like in PCB where we have cores and prepregs, you have adhesive and clads in flex. Again, the fabricators are very good at putting these together to make a flexible PCB. And I think we're pretty much on time.
Oh, wonderful, Chris. Well, hey, we're going to do some questions, but before we do, I'd like to thank everybody for joining us today. I know it's just about hitting the top of the hour. Next week, we've got a presentation in our Talk Teach Tech Thursdays on solder pastes with Sebastian Weber and Shane Sheffield. So if you'd like to join us for that, please do. Also, we are recording this presentation and we'll make it available at royalcircuits.com/blog within the next day or two. And in that, Chris, is it okay if we include your slides? A lot of people have been asking for those.
Yes, yeah. I probably will need to convert it to Adobe just because the file size is large, but yeah, that's not a problem.
Okay, I've been trying to one of the reasons my interaction's been I've been trying to keep up with the questions as we go. So the good news is we've only got 9 open questions, and not all of them are really open questions. So we're going to get out of here pretty quick. First question that we have, it relates to way back in the presentation. How does lower decay relate to resistance in small spaces?
Okay. So I'm going to answer the question the way I think it was intended. If you lower the dielectric constant, you can make the trace wider and maintain the same impedance. So in other words, if I were to look at FR4 with a dielectric constant of about 4, and let's just say I have a 3 mil space between the trace and thickness, 3 mil thickness between the trace and the reference plane. If I lower the decay of that 3 mil dielectric, I can make that trace wider and hit the same impedance. That would lower the DC resistance of that trace. I hope that answered the question.
Hey, I didn't even really know what they were asking, so I'm going to say that's good. Thank you, sir. From Eric, we ask, what are the 9, I don't know why we picked 9, we must have mentioned that at some point, but what are the 9 most common materials that you offer? What are your most commonly purchased
So we have two flavors of FR4. One, the higher filled economical version called 185HR. The 370HR has been our kind of our mainstay product. It's been around for about 15 years, and we sell a lot of it. So that's our most common product. Then we have something called 408 HR, which is a mid-loss, mid-decay material. Then iSpeed, which is a little bit better performing than 408 HR. Then after iSpeed, we have iTerra MT40, which is a even lower loss, higher performing material. It's used for both high-speed digital and RF. We have Tachyon 100G, which is a low decay, low loss material for high-speed digital. We have Astra MT77, which is used for RF applications, even lower in loss than Tachyon. We have Polyimide Material, both a flame retardant version and a standard version. I'm trying to think if I missed anything. I think that captures the most common materials. We still sell some FR406. That's a pre-lead-free assembly material. Again, that's primarily for legacy. And then there's a bunch of others like A111 and IS415 and others. But the main materials are the ones I talked about: 185, 370, 408 HR, iSpeed, iTerra, Tachyon, and Astra, and Polyimide, the two different Polyimide flavors. Those are the most common materials we sell.
All right, thanks, Chris.
Yeah, go ahead.
Next question is, at what edge rates should we look past FR4? So at what point do we start?
Well, depending on the design, bit rate, I think the question was, right?
It says edge rates, so I think they're talking about, rise fall times.
Yeah. I would say between, I'm going to give a big range, between 2 and 5 gig. It really depends a lot on what the design will tolerate. But I would say the ceiling is somewhere between 2 and 5 gigabits. You have to start thinking about things like FR408 or 408 HR and iSpeed. And then when you go beyond that, let's say the 5 to 10 gigabit range, you might want to start thinking about something like iTerra MT40.
Okay.
Good up to 25 gig, and then beyond that, you would go to something like Tachyon.
All right, thanks, Chris. We've got a question. What about roughness induced by fabricators in MLB bonding?
Oh, great question. There is an alternative oxide bonding process, and I won't go into the details of how that works, but that does provide some micro roughening to improve adhesion. If done properly, that should only produce about a 2 micron RZ. If it's done excessively, that can be a big problem. So that's a great question, and it's something the fabricators need to watch in their process. One of the things that you can't do, and it's important for the fabricator to know what the design can tolerate. There are some cases where, let's just say the process is done, and for some reason you end up with some stains on the surface, and you want to rerun it through the alternative oxide bonding process. You can't do that on high-speed digital if the bit rate's high. So it's something important that the fabricator should know up front, and it is something that has to be closely monitored. It's also an issue in flex, not for both speed, but also for flexibility. If you overdo the bonding process, you can end up with circuit cracks. So that's where, again, where the fabricator needs to have good process controls, and we can always help with that.
All right. So here's a question, and I don't know how we'll answer this. We might need to just save it and answer it in text, but do you have any studies showing copper roughness contribution to the loss for RF applications?
Yes, actually, I do have some of that data.
Wonderful. So email Chris at chris@inselectro.com, and I'm sure he will be happy to help you out there. What are the this is always a fun one. People always want to know numbers. So what's the cheapest flex or rigid, or it says semi-flex material?
So there are some FR4s that come with a higher ductility copper. I would say that in general, they're cheaper than something like Pyrolux, which is a copper clad Kapton material. They're not widely used because their flexibility is very limited. In general, though, if you need something that's flexible, stick with 1 mil dielectrics. If you don't need them for other purposes, like for instance, you need a certain amount of spacing for impedance or a particular strip line design. If you could stick with 1 mil dielectrics, that will lower the cost of the circuitry substantially. When you get above 2 mils, the cost of film-based flexible dielectrics really increases. So if you stay below that 2 mil threshold, the cost is much more manageable. But if it's a bend it install and the radius is big, you could use 2 mil FR4 in some applications. Just proceed with caution.
All right, and with that, I would like to thank Chris very much. And you really do have an encyclopedic knowledge, buddy. I know you're very modest, but I'm always impressed every time I talk to you. Honestly, I have trouble keeping up. It's that great. So please come back anytime. Next week, just to remind you, we've got Sebastian Weber and Shane Sheffield talking about solder pastes in our Talk Teach Tech Thursdays. And one of our friends, Dr. Eric Bogaton, is giving a talk completely unrelated to us later today with the Teledyne LaCroix series of webinars. And in my opinion, anytime that Dr. Bogaton speaks, it's just not to be missed. So if you guys are looking for something to do, I think that starts in either 1 or 2 hours. Just check in with Teledyne LaCroix. All right, I'd like to thank again everyone. We will post the slides and the webinar within the next several days at royalcircuits.com/blog. And if you have any further questions, please feel free to reach out at Lisa at royalcircuits.com, Allison at royalcircuits.com, or C. Hunrath at inselectro.com. Thanks again. Have a wonderful day and be safe. Take care all.